Hello, welcome. I'm Yuki. Welcome to our second episode of our stream processing. Let's get started right away. In this episode, we will mainly discuss the selection of streaming processing technology solutions. Without further ado, let's dive into the topic. First of all, in our scenario, we will use data fusion, which is similar to Spark SQL. It's a batch processing engine in terms of content type. Currently, we aim to build a stream processing engine on top of it. Well, in the open source world, there are two popular stream processing engines. One is Spark's structured streaming, and the other is Flink. We have drawn inspiration from both of them. However, structured streaming essentially reuses Spark SQL's batch processing engine. So it's somewhat similar to our current requirements and use cases. So it's more relevant. In this section, we'll mainly discuss structured streaming. Why do we decide to build our stream processing engine based on it? Let's talk about its implementation. Some key features of structured streaming processing are that it's an incremental query and model. It has some characteristics. Primarily, it's designed for near real-time processing. Although it also supports real-time processing like Flink. However, the real-time mode is still experimental at this point. So for now, we are focusing on its micro-batch mode, which is akin to near real-time. For example, its incremental query model essentially reuses Spark SQL's batch processing engine. And the reason is that Spark SQL has been around for many years, and it has a series of optimizations. So, building a streaming processing engine on top of it not only covers batch processing, but also stream processing. And many optimizations can be reused. It offers two processing modes, near real-time and real-time. Let's focus on near real-time for now. Structured streaming's characteristics include it cuts the stream into small batches, so it processes data in small increments at fixed intervals. This is why it's called VP mode. It doesn't provide real-time processing like Flink. Let's skip the real-time mode for now. The next slide provides an overview of this VP mode. The VP mode in near real-time processing introduces a certain processing delay. If you look at the timeline on top, it shows the actual time events occur. And the solid line below represents where our processing engine handles the data. The VP mode triggers processing at fixed intervals, as indicated by the purple dashed line. In this VP processing mode, because of these fixed intervals, as shown by the purple dashed lines, the first time it triggers, it processes the 3 data points before it. And the second time indicated by the second purple dashed line, it processes the 4 data points before it. You can see that, for example, the blue data point. Its actual arrival time is quite early, but there's a significant processing delay before it's actually handled. Now, let's take a look at the real-time processing mode. In the real-time mode, the processing delay is much smaller. As soon as a data point arrives, it's processed immediately. So, the real-time mode has very low latency, but it might require more substantial modifications to the processing engine, which may not be necessary for our current scenario. We don't need such substantial changes, because for our use cases, the VP mode completely meets our requirement. Moreover, this VP mode entails relatively small changes, both in terms of the scenarios requirement and cost. So, VP mode is our preferred choice. We'll briefly explain why we choose the structured streaming VP mode. Next, we'll provide a basic overview of some key concepts in structured streaming. First, we'll look at the input and output, which are crucial in stream processing. In structured streaming, which is a stream processing framework, input data and processing it, as well as outputting result, are vital steps. Structured streaming natively supports many connectors, meaning it can connect to the various data sources. However, in stream processing, you may be familiar with different semantics, such as exactly once or at least once processing. To ensure this semantics, certain conditions must be met. For example, the data source must be replayable, like Kafka, where you can specify offset to read from. This allows you to continue processing from where you left off if your program crashes and the system goes down. It avoids reprocessing the entire data from the beginning, which would waste resources and increase cost. Additionally, output requirements include idempotent writing. Idempotent writing means that if you output the same data multiplied, the result should remain the same, rather than appending the data repeatedly. For instance, if you repeatedly output duplicate data, the result should not change, it remains the same. This is what we mean by idempotent writing. Furthermore, some specific things in structured streaming implement exactly once writing to ensure the desired semantics. For our CnosDB, it inherently supports this because it's a time series database. In a time series database, data within the same series and timestamp is deduplicated, which aligns with the idempotent writing requirement. Additionally, structured streaming's API is entirely consistent with SparkSQL's batch processing API. This means that users only need to learn one set of APIs, allowing them to work with both batch and streaming processing. Moreover, structured streaming supports various output modes, such as append, update, and complete. We'll dive into the differences between this mode later. This mode determines which data should be output and when. Additionally, there are some unique APIs like triggers, which are essentially because structured streaming operates in periodic intervals. A trigger initiates the execution of your queries, and the watermarks are crucial in stream processing. They decide when immediately state data should be cleaned up and which delayed data or data that arrived too late should still be allowed for processing. We'll discuss this concept in more details later. I won't go into further detail for now. Now, let's move on to the execution. It essentially reuses the batch processing engine. Because it's relatively straightforward to adapt it for the VP mode. Another aspect to consider is fault tolerance. Because stream processing tasks run continuously, it's possible that a machine may crash during execution. We need to ensure that when the machine recovers and the program is restarted, it can resume processing from where it left off before the crash. This requires mechanisms such as WL, write-ahead logging, or checkpointing to maintain fault tolerance. We have provided a brief overview of these topics. Next, let's take a look at the high-level design of the stream processing model. Since SQL engines typically deal with tables, stream data sources can also be considered as tables, but with continuously arriving data, like an unbounded table. Over time, the number of records in this table keeps increasing. You can think of it as an infinite table, with record continuously being appended. Let's move on to the next section. This is a relatively simple processing flow, demonstrating how it works with streams. I've taken this diagram directly from the official Spark website. It's better to use their diagrams now. They are quite good. Here you can see a timeline with 10 ones, 10 twos, and 10 threes. When we have 10 ones, a batch of data arrives. At this point, our batch processing, which runs periodically, handles this batch of data and stores it in a result. You can think of this result as an immediate state for now. Later, I'll explain it in more detail. When we have 10 twos, another batch of data arrives, and the processing result is again saved as an immediate state. Then, when we have 10 threes, our repeat processing engine handles this data and saves it in this state. The output represents our decision regarding which data from this immediate state needs to be outputted to the downstream sink, and at what point in time this data should be outputted. This relates to the output mode I mentioned earlier. We'll dive deeper into this in subsequent discussions. So what we have here is a fundamental flow. Similar to this process, data continuously arrives from the source, and our processing periodically handles it. After processing, it enters an immediate state, and generating output requires certain strategies for selection and decision making. In essence, it's a relatively straightforward model, but there are many details within it, which we'll discuss in more depth later. You can see that this model is quite straightforward. Within this model, we have provided an overview of the process. First, let's talk about input. Input essentially represents an abstract representation of a data stream. There can be various types of input sources, all confronting to an interface. In practice, you can have multiple types of input. We'll define this input based on certain method and attribute we will discuss later. One essential attribute is the offset, which helps tracks the reading precision. Processing involves incrementally queries of input. The processing is triggered periodically. Speaking of which, WL, write-ahead law, is a key concept. Each time processing is triggered, the data and its offset are locked into the WL. Furthermore, the result generated by the query for a batch of data are stored in the result table, serving as an immediate state. Additionally, the output from this result table requires specific strategies, and once outputted, it needs to be logged in a commit log for fault tolerance, like the WL. Now, let's delve into some further considerations regarding this conceptual framework. Let's continue exploring together. Suppose we are performing a 10-minute aggregation operation within a process. How should we go about it? And what problems might we encounter? Let's assume we have a gift here. This is the reason, and below is a timeline. At 12:52.10, we have periodic triggering of the calculation operation. Before 12:05, we receive two data entries. Each entry consists of a timestamp and a string with a word like cats and dogs. Our task is to count the occurrence of each word within 10-minute intervals. So at 12:05, we perform the count, inputting data from 12:02 and 12:03, which fall within the 12 and the 12:10 window. We record the count. For example, cat appears once and dog appears 3 times. By 12:10, we only need to process the new data, as the previous data was already handled by the 12:05 operation. This is an incremental process. After processing by 12:10, we receive data from 12:07, which also falls within the 12 to 12:10 window. In this window, owl appears once and cat appears twice. We updated the state for dog as it appears again at 12:04. By 12:15, we perform another count. However, we encounter a red data point at 12:04, which should have arrived earlier. We need to deal with this delayed arrival. After processing by 12:15, we handle the delayed data from 12:04, and dog now has a total count 4. This is a simplified process. You might notice a couple issues. 1. How long should we wait for delayed data? And do we need to process all delays? If you decide to process delayed data, how do we handle it? For example, dog at 12:04. We cannot keep state indefinitely, as that's impractical. Handling delayed data involves some trading offs. If data arrives within significant delay, it might no longer be useful to process. Thus, two problems arise: handling data delay and managing state. We can't keep state indefinitely to avoid memory exhaustion. The environment poses challenges since stream processing is a persistent task. If our program crashes or the machine fails, we want to continue processing from where we left off at a certain time, not reprocessing everything before that time. Keep this question in mind as we move forward in our discussion. This covers the topic of handling delayed data. We previously mentioned the issue of handling delayed data. So, how should we address this problem? In stream processing, there is a concept called watermark that helps us deal with the delayed data. This watermark can filter out data that arrives later than expected. In other words, if data arrives too late, we can discard it. Additionally, we use watermarks to clean up our immediate state data because we can't keep it indefinitely. So we need something to control this process, and that something is a watermark. For now, you can get a basic understanding of this concept and its process purpose. In the future, I'll explain how watermarks are implemented and how they work. Now, let's move on to the topic of fault tolerance. As mentioned earlier, one of our challenges is how to handle fault tolerance in stream processing. In stream processing, there are several mechanisms for achieving fault tolerance. The first mechanism is related to the stream source. Stream sources are required to have offsets. This means that they can provide data based on offsets, allowing us to continue reading from where we left off after restart. This helps us maintain normal processing states even after a machine restart. The second mechanism involves recording data as we process it. Typically during batch processing, we use write-ahead log (WAL), save immediately read state, and record commit logs. This set of operations ensures that we can restart our program and continue processing from an offset where it crashed. We can also retrieve and merge our immediate state, ensuring that no data is lost. The third mechanism pertains to the stream sync. It requires that the writes be idempotent, meaning that writing the same data multiple times has the same effect as writing it once. This enables data synchronization and allows for data override, preventing data loss during restart. The specific details of this mechanism will be explored in more depth in the future. For now, it's essential to understand the approaches we use to address fault tolerance. Within this batch processing engine for stream processing, there are certain operations and limitations to be aware of. First, it supports most SQL operations commonly used in batch processing. The majority of supported operations are applicable to batch processing. However, some operations, like multiple table joins involving multiple time windows, are not supported due to their complexity. Concepts such as limit and offset are not meaningful in the context of streaming because streams are inherently unbounded, and limiting or offsetting them doesn't make sense. The distinct operation is also not supported because it's a global operation, and streams are unbounded by nature. The order by operation is not supported unless it occurs within an aggregation operation that's synchronized within the aggregation operation and meets certain output criteria. While there are certain limitations, these operations are not commonly used in practical streaming scenarios, so the impact of this limitation is minimal. Streaming processing differs from batch processing in terms of drawing semantics. The course doesn't intend to dive into the details of these differences, and support for complex drawings may be considered in the future if there's a demand. It's important to know that the course won't go into deep details regarding these specific limitations, as they fall outside the scope of the current curriculum. Now, let's dive into the processing flow using an example. First, we'll talk about aggregation operations without watermarks, which are similar to batch processing operations. We won't go into details about these operations for now, but they may involve some immediate calculations. Instead, we'll focus on event time in streaming processing. Now, let's dive into time-based window aggregation operations. Window aggregation is a typical and a widely used scenario in stream processing. We will use scenario to explain the concept. Window aggregation operations in streaming are quite similar to those in batch processing. They involve maintaining an aggregation state for records associated with each time window. In this example, we continuously read records from a socket, and each record contains a timestamp and a word. We use a 10-minute window to count the occurrence of each word. The windows slide every 5 minutes, creating a sliding window. The triggering interval for our batch processing is set at 5 minutes. Let's take a look at the diagram below, which resembles the one we discussed earlier. Now let's dive a bit deeper. The input stream is the same as what we saw before. The triggering period are at 12:05, 12:18, and 20:15. In this case, we will focus on how the embedded state changes after each batch processing cycle. After the first cycle at 12:05, the records from 12:02 and 12:03 are within the window of 12 to 12:10. The word cat has a count of 1, and the dog remains the same. When the next cycle happens at 12:10, the word owl appears in a different record. The window 12:05 and 12 to 12:15 is a new window, and the count are updated accordingly. At 12:15, the records from 12:04 are processed. Since that is a delayed record, it also falls into the window 12:05 to 12:15, thus the count are updated. This example illustrated how a sliding window aggregation works on a stream. However, it doesn't cover aspects like data latency, state eviction, and output mechanism, which we will explore later. Now, let's extend this example to input delayed records. In this scenario, a record within a timestamp of 10:4 delay arrives after 12:10. It's considered a delayed record and needs to be processed. This detailed explanation of the diagram helps us understand the flow of processing even better. This chart right now, because of this chart, it might seem a little complex. Let's start by examining this each point and the line inside it. What does it represent? First, take a look at the horizontal and vertical axes. The vertical axis represents our timeline. The vertical axis represents the event timeline for this data, the time associated with the data itself. For example, the time when the data was generated. Like this data here, this yellow point. Well, this yellow point represents normal data. It means there's no delay. Now, this red point represents data with some delay, but it's not significant. However, it's still within the data acceptance range. This blue line is the maximum event time. It's the line of time, the maximum test time. This maximum event time will be used later when we calculate the watermark. Though we haven't discussed that yet, when we calculate the watermark, we will use this maximum event time. It will continue to be important, so we will emphasize it here. But this red line is the watermark. This red line represents the watermark. Now, let's dive into the detail of this chart. If you can understand this chart, you will get a cleaner picture of the entire stream processing workflow. Of course, there might be still some confusion. This chart took me a while to grasp initially as well. Of course, some parts might still be unclear. because when I first look at this chart, it also took me a while. Okay, let's move on. Now let's take a look at the trigger cycle. Does it trigger once every 5 minutes or how often? Is it triggered once every 5 minutes? For instance, before 12:05, there was no data to retrieve, so the immediate state table was empty. But at 12:10, you can see that just before that, we received 2 data points. One at 12:07 labeled DPG, and another around 12:10, 12:08 labeled CAD. So our immediate state table now looks like this. We have RO and G1 corresponding to the time window from 12:05 to 12:15. We have 10-minute window that slide every 5 minutes. So this 2 data point falls into 2 different windows. You can see this blue line here. This blue line represents the current batch's maximum event time, which is important for watermark calculation. Although we'll discuss that later. It shows the maximum event time in the raw data we have processed. This maximum event time is crucial for calculating the watermark. But we haven't reached that part yet. So let's continue. Moving on to we received 2 more data points. One is at 12:04 labeled DAR, and the other is 12:09 labeled CAD. You can see that is 12:04 is marked in yellow, indicating no delay, while 12:09 is marked in red, suggesting some delay. The 12:09 data point represents its survival time, but it arrives after 12:10. So it has a delay, but we will still process it. Why? Because as of 36:03, it falls within the acceptance window for watermark calculation, which we will explain later. After processing the data, we need to update the intermediate state table. You can see blue and gray bars here, where blue represents updated data and gray represents unchanged data. At 37:09, we update the CAD entry because as the nice CAD record from the window has been processed. You will notice that we no longer update the CAD entry because the 12:09 data falls within the time window from 12:05 to 12:15. Similarly, by 37:41, the DAR data is updated at 12:14. Finally, at 38:04, we calculate the maximum event time. In this case, it's 12:14 because the previous batch processed data within that timestamp. This is used in watermark calculation. Speaking of watermark calculation, we calculate it by subtracting the maximum acceptance delay, for example, 10 minutes, from the maximum event time. This defines the timestamp until which we can accept data in the next batch. For example, if our maximum acceptance delay is 10 minutes, the next batch can accept data generated after 12:04. Data generated before 12:04 will be discarded. To summarize, at 38:46, we discard the 12:04 data because it had too much delay and may only consider the 12:17 data. This is reflected in the updated state at 38:55. I hope this helps clarify the graph. If you still have questions or if I explaining something, please feel free to ask. Understanding this graph is key to grasping the stream processing workflow. Alright, if you haven't understood it, you can ask questions in the chat. If it's clear, I feel like I've covered about half of it. We might have to cover the remaining half in the next session or the one after that. Because there's quite a bit left to cover, and our time might not be sufficient now. Actually, let me go ahead and finish up the remaining part first. After everyone has seen the processing flow of this program, let's take a look at the various types of windows it actually supports. Let me quickly explain here. One is tumbling window. Then there's a sliding window. There are also session windows, tumbling windows, and sliding windows. Actually, these are quite easy to understand. Let's start with a tumbling window. So, a tumbling window is one without overlap. You can see these are time windows, for instance, from 12 to 12:05, then from 12:10 to 12:15. This is a 5-minute rolling window. Now, a sliding window is different. A sliding window can overlap. Just take a look at this window. You can see that this window overlaps. So here, in this graph, we have a window of size 10 minutes. And it slides every 5 minutes. For example, this is a sliding window. Then there's a session window. A session window has a parameter here. In this case, the maximum gap time is 5 minutes. For example, if we look at the time from the arrival of the last data point until now, if there is no data arriving within 5 minutes, then this window will close. For example, in this window, W1, you can see that at 12:09, the last record arrived. 5 minutes later, that is at 12:14, no data has arrived. So this window is closed. This is a session window. In addition to this, we just mentioned, in addition to these 3 types of windows, there is also the state window. The state window is used in stream processing and also in time series scenarios. It's quite common in this context. Of course, we'll extend experiments in CnosDB. But I won't go into that specific here today. Now let's move on to each type of window. Its definition, characteristic, and implementation. As we mentioned earlier, we give a rough overview of what the window is like. So we won't go into the details here. Thank you everyone. As you all know that our CnosDB Cloud beta is alive now. Welcome to join our Discord channel below, and you can explore more. I'll see you. Bye bye.